So second session Sunday morning is very much about video and cameras and things, and it's our regular session with Brian, who's going to talk to us this year about the lenses that we use. Over to you, Brian.
Thank you very much. Well, good morning everybody. The lenses on a camera is very often neglected. We're more concerned with what comes out of the camera perhaps, but what comes out is greatly dependent upon what goes in. So we're going to have a look this morning, a quick look at some of the parameters of lenses and what some of the terms mean. And when I started to explore this, it turned out to be a much bigger subject than I thought. I know all about diff gain and diff phase and all sorts of exciting video terms, but there's an equivalent lot of errors and deficiencies of lenses, as we shall perhaps see. So that thing is outside. I'm sure you've all seen it, and that's a much more modern descendant. And they all come in different sizes and different sensor sizes. The size of the CCD or the tube has a big bearing on the size of the lens. And that one has 25mm tubes, and I think that's a 2/3 CCD. And there's two great distinctions between lenses: there's zoom lenses and fixed lenses. And that is a fixed lens. A removable lens such as this gives you more choice. And the camera outside and most modern cameras that are used professionally have interchangeable lenses so that you can choose a lens to suit the purpose in hand. Think to yourself why a professional photographer will probably choose an SLR camera so that they can select the lens according to the use. And going back to the previous one, you're stuck with the range of that lens largely, and there's no choice, but it has other advantages. It's very convenient. So the first parameter I want to look at is what's called the focal length, and that is the distance between the glass bit and the sensor bit. Lenses which have a long focal length have a narrow angle of view, and vice versa, a short focal length camera has a wide angle of view. This lens is a 3-inch, and that makes it a medium sort of close-up lens. So here we have a view of a schematic of the lens. There is our subject, and there is the image on the sensor. And that distance there, the focal length, and the size of the sensor gives us a formula here which we can calculate the angle of view from. There won't be too many formulas, don't panic. As you can see, as f becomes smaller, the angle of view increases because f is there, and as y changes, that also affects the angle of view. The other principal parameter of a lens is the aperture, or in simple terms, the size of the glass. The more glass there is, the more light that can be gathered. Then we have the iris. That controls the effective diameter of the lens, and when there is adequate light we can reduce the iris. And going back to our previous slide, no, forget that, that's rubbish. As we reduce the amount of light that is emitted, we're closing the iris, and the word which is often used is to stop the lens down. I say stop because you'll have noticed that lenses have numbers on them, and this is the F number. Typically 1.4 is the widest setting which is seen, and that admits the maximum amount of lens, and that can be reduced to typically f22 in a root 2 ratio. So each stop is a root 2, and that halves the light admitted. Confusingly, we have f there for the iris and we have f there for the focal length. Why? And these are related by this formula which Windows has garbled. But if you can just make it out, we have the iris setting there, the f number, the focal length and the diameter of the lens. And from the focal length and the effective diameter we can create an f number. Now the iris setting also has a bearing on what we call the depth of field. Now it's difficult to explain perhaps, but if you look at one extreme, which is a pinhole camera, whereby we have a subject, a pinhole in the our shoebox and a piece of translucent screen on the back, and we have an image. We've perhaps all done this at school. But the interesting thing about it is there's no focus control, but the image remains sharp at whatever distance. That's because the effective aperture is very small. The depth of field tends to be infinitive. This idea is also used on some small cameras at the cheap end of the market that have no focus adjustment. They rely on the fact that the aperture is quite small to give the depth of field so that the focus control is not required. But it only really works for small apertures. This is perhaps a more practical illustration of a camera and the depth of field. With a real lens of the type we use, the depth of field depends on both the aperture and the focal length. There is a formula for this, but I decided it was too complicated. But simplistically, we have the subject which is sharp, and subjects in front of the focus point will be blurred and behind. It's interesting to note that the distance behind is larger than the distance in front, and the area which remains in focus is what we call the depth of field. The key things are, as the aperture gets larger and the angle of view smaller, perhaps by zooming in, the depth of field reduces. Here's another word which you only see related to lenses: hyperfocal distance. And that refers to the distance behind the subject which is sharp, which can tend to be infinite. And here is an illustration of the problem. On the left we have a scene shot with the lens at f4, and Larry the lamb is quite sharp, but Felix the dog is going a bit soft, and their owner is quite soft. And the measure there gives you an indication of the depth of field, and really it's, these are inches, 5 to about 8 inches, so the depth of field is only 3 inches in that particular illustration. It is an extreme one which I've set up to show the shortness, how short the depth of field can be. And this is the same shot at f22, and you can see that the depth of field is pretty good. And apart from artistic effects where you might want the background to be very soft, most of us would want most things to be in focus most of the time. So the solution is to operate on a small iris setting, operating perhaps at f16, f11, and the way to achieve that is to put adequate light on the scene. which brings us to another interesting area, and that's iris. That's me, ugly brute. But there I am, more or less correctly exposed. I tend to think I'm a bit pink in the face, but never mind. And our cameras are often left in auto iris, and for the large part that works, unless there's a wide range of brightness, and that is exactly the same shot, except I've turned the light on. And you can see there that the auto iris has made the light and the book bright, but has made me dark. So when you're setting up a scene for your transmissions, you need to have some consideration as to what's in the background or the side, so that you avoid the subject being underexposed or overexposed. Now, here's another term. It's really, we're back in the camera now with shutter, but the iris controls the amount of light which might arrive at the sensor. Now, in an old tube camera, the light arrived for the frame period and it was accumulated, and as the beam passed over, it read out the charge which had been accumulated for that period, and that was it. That's what you got. But with CCD you have another option. CCDs, because they're under control and you can actually select when you read out the information, you can read it out early and throw away some of the collected light to obtain a shorter exposure period. And because the exposure period is shorter, less light has come in, and it has a similar effect to closing the iris. It gives you another method of control. And you will often see that domestic or small simple cameras will use shutter in lieu of auto iris, because auto iris requires an iris and a motor and expense, where shutter is a bit of software and easy to do. And that sort of works, but it can give you unusual motion. When you're viewing a scene and it's stationary, it doesn't matter what the exposure period is, it's the same shot, things are in the same place. But if things were moving within that period, with a tube camera or a CCD which is not using shutter, the light accumulates over the field period, and as you move an object, there'll be a certain amount at the beginning of the collection period where your arm is there, and as it moves it becomes blurred. Now, you might think you don't want that, but it does give a natural appearance to pictures. When you introduce shutter and you only collect the light for a short period of frame period, say that will be frame 1, and the next frame your arm might be there or there, and there's no blur in between, and effectively your arm goes from there to there magically without this intermediate blurriness. Now, sometimes that's good, especially if you want to do a slow motion replay, and sometimes it leads to an unnatural appearance of objects because your eye automatically does the blurring when you view a scene. So shutter can be bad and it can be good. It's art, really. Now, lens adjustments. The first one, well, that's self-explanatory, and there's usually a knob for it. Focus, depending on what you have, there may be a knob for it or there may not be. It may be automatic, or it may be tending to be a pinhole camera where there is no focus adjustment. The iris we've spoke about in the previous frame, and the object of an iris adjustment is to achieve a correctly exposed image with the depth of field that you require for your particular shot. Now, this fourth one is something that you may not be aware of. It's called back focus. Now, when you have a zoom lens compared with a fixed lens, we've spoke about the focal length, which is fixed. The focal length on a zoom is variable, and that is done by moving the glass elements inside the zoom lens. But in order to maintain focus, that's focus of the image over the zoom range, the distance between the back of the lens and the sensor needs to be adjusted to the manufacturer's specification. If it's not correct, as you zoom, the image will not remain in focus. It will go focus and come out the other side. And that's operationally disadvantage. So this back focus adjustment needs setting if you have interchangeable lenses. If you have a camera with the manufacturer's installed built-in lens, that will be done at the time of manufacture. And we'll have a quick look at how it might be adjusted. And this would be the process which would be used on the broadcast camera outside as they change one lens for another lens. So the first thing you do is to set the iris fully open. Remember in the previous slide how we discussed that when the iris is wide open, the depth of field is short. And to make this adjustment, you need to be in that short mode so that it becomes more obvious where the correct point is. So we zoom into a distant object, or at the distance recommended by the lens manufacturer if we can bothered, or just a convenient distant object. And then you focus with the focus control for the lens to make it sharp. And then zoom out without touching the focus control. You adjust the back focus to achieve the best sharpness, and you may have to go around that loop twice just to get it correct. And when it's done, when you zoom in tight to an object and focus and then zoom out, the whole field should remain in focus for the complete zoom range. That's the back focus adjustment on the big camera outside, and there's adjustment control there and a locking screw. This little lens here is a bog standard C format zoom lens we've all seen them, but there's no actual adjustment for back focus, and it was often done by moving the sensor. Easy to do with a tube, harder with a CCD, or sometimes there would be some sort of mechanical gubbins that did the back and forth adjustment. Now then, image size. In one of the earlier slides we discussed why, the height of the image, and the bearing that has on the focal length of a lens. So an old-fashioned image orthicon tube is basically 35mm format with a diagonal of 21.4mm. The later Vidicon tubes had a 16mm diagonal, and as the world progressed, tubes shrank to 17mm with an 11mm diagonal, and then down to 12.5mm tubes, and also CCDs now with an 8mm diagonal, down even further to a 5mm diagonal. And one of the great advantages of this was that you needed less glass, less expense, tick. Beyond a third of an inch, there's little standardization. Quarter inch is quite popular, or down to a vanishing point. I don't know what size the sensor is in an iPhone, but it must be quite small because the lens is quite small. It's worth having a quick mention of aspect ratio. aspect ratios caused enormous confusion. In the old days we had 4:3 and everybody had 4:3 and there was no problem. But the world moved on and it was decreed that 16:9 would be a good thing. But the cameras had 16:9 sensors and the tellies at home had 4:3 screens and any permutation you like out of that. So there was a certain amount of confusion. But the important thing to remember is that a circle in the scene is a circle on your screen at the receiving end. Now, it's unusual for you to be able to change the aspect ratio of your camera. It would either be 4:3 or 16:9. And that's largely what you recorded or sent. That led to problems, as I said, when there was a difference in the viewing screen. You had short and fat or tall and thin. The lens itself, is worth mentioning, doesn't care what aspect ratio you're using, providing that the diagonal that the lens will produce on the sensor is not cropped. The common arrangement was that the width of the image on the sensor was more or less the same, and when you went to 16:9 the actual sensor didn't get wider as it appears to be. What it happened was it became less tall. They would of course put more pixels in, but the physical size of the image that was focused by the lens onto the target was much the same width and less height. To do it the other way around would have cost more money. Moving on to the next slide. So there's no easy solutions if you're in the wrong aspect ratio. All of the solutions are either expensive or undesirable. If you have a 4:3 to 16:9, if you're looking at it on a 16:9 monitor, the best solution is to reduce the width of the display by winding what we would call in the old days the horizontal scan in. If you've got a flat screen display, it's harder. There may be an option to reduce the patch. And similarly, 16:9 to 4:3, the easiest solution was to reduce the height of your monitor display, the vertical scan. There are electronic solutions which deal with it that letterbox or pillar box the picture depending on which way we want to go. We've all seen the example of the widescreen film whereby there's a black bit at the top and a black bit at the bottom and the picture is more or less right, but you're effectively wasting the resolution in that top bit and bottom bit as you've thrown it away. And there are any number of permutations where you crop the picture and pan and scan, but they're all unsatisfactory in one way or another because they lose information or they lose resolution. Now, I thought at this point we might take a little diversion and have a look at the history of the zoom lens. This is a very early one. Made by Watson and Sons of Barnet, and the design came from H.H. Hopkins, and it is the brand new 5:1 zoom lens, appreciably greater than its predecessors, and well, it was revolutionary at the time, but we look back on it and go, ugh. I particularly like the chain drives. And at the back there is the wedge plate where the camera would sit. So the camera will be like that. And there's this enormous aluminium sledge that the whole thing sat on. Revolutionary at the time. This is a couple of 3 years later, and it's still a basic 5:1 range, but it's much more friendly in shape. That bolts straight onto the front of the camera, and there would be a couple of rods from there up to the camera to support the weight. And it had a 5:1 range, but it had this lever at the back here, a range extender. So you could flick that quite easily, and that gave you either 4 to 20 inches of focal length or 8 to 40. And it was well suited to outside broadcasts. Moving on a few years further, and this is a 10:1 range zoom, and I've shown here the mechanical controls. That's the focus and that's the zoom, and there would be a Bowden cable arrangement that went from the connector there to a connector on the zoom lens, so you could sit at the back and quite happily twiddle away, and the chain drives have gone. Moving on again, and we've got servo motors, and that was, from the broadcaster's point of view, that was a big step forward. All this sort of jerky Bowden cable or chains have gone, and you've got servo motors and amplifiers to worry about, and feedback loops. There's the pot there that transmitted the position back to the servo amplifiers, and a connector that went off to an interesting heavy box full of amplifiers. But 10:1 range still, and note the maximum F number there was 3.8. This is a cutaway of a similar lens, in the style of how the automobile people expose their pistons. Here we're exposing the glass elements and all the concentric tubes that slid according to the zoom angle that you required, and it's really quite complex. They twist and slide in and out on the pegs, and this one was done at Television Centre, the BBC Television Centre, as a teaching aid. I understand that it did actually work. You could connect it up and see the parts move inside, keeping your fingers out of it. That's the lens that's on the camera outside. We've moved on to the mid-70s now, and it has a 15:1 range at f1.7. Where's my spot gone? Battery's flat. Oh dear, where's the stick? Thank you, Kevin. Oh, it's changed colour. It's really quite a tidy lens in a lot of ways. It's been engineered and tidied up as time goes on, and the servo motors and the servo amplifiers are in two black boxes underneath there, and they're dead easy to change. There's just a clippy thing at the back, and it's a moment's work. But going back to the f1.7, compare that to the slightly larger lens we had in the previous slide, which was f3.8. Zoom lenses have a disadvantage when they go tight in. Comes out of the mathematics of the formulas we were looking at for the F number, the one that got garbled. The problem is referred to as ramping, and whilst the lens may be f1.7 at wide angle, as it zooms in, there'll be a certain point where the F number changes, and as it goes in tighter, it will effectively let in less light and less light, and that's very tedious. But if the iris happens to be, say, at f8 for the particular light level involved, and you zoom in, you won't notice the ramping, because it might ramp to f4 or f5, and that's still within the f11 or f8 range, so you don't notice. You only notice it when you're wide open. For those of you who know me, I've spent many years on outside broadcasts, and it always used to be very annoying because the camera you would be controlling would be looking at the pitch, and the pitch is floodlit, and it wasn't so bad. But the cameraman would decide to offer a different shot, and he might go into the back of the stand or look at the manager, and of course to get head and shoulders of the manager he's going to zoom in dead tight. The lens would ramp and there wouldn't be enough light, and it would be dark and earache. Anyway, that's another story. This is a little early ENG lens for the on the shoulder camera, and in there is the iris motor, but the focus and the zoom are operated manually. And this is a much more modern ENG lens of recent manufacture, and there's a control there to operate the zoom lens. The zoom lens is now motorized. The focus is still manual, and that's the iris ring there, which is driven by another motor controlled either by the auto iris circuits of the camera or the vision operator back at the control point. And now I'll just go back to the previous slide for a moment. You'll have noticed the lens hood there, which most lenses seem to have, and ask yourself what that's for. Lenses aren't perfect. Those of us who wear spectacles perhaps know about the disadvantages. When they're less clean than they might be, you get interesting results, and lenses suffer from the same thing. Now, the lens front element is there, and this is the lens hood. Light which enters the lens from the subject is focused onto the sensor, no problem. But a bright light off to one side will cause problems. If the lens hood wasn't there, the light might enter the lens at that angle and be internally reflected, perhaps once or twice, and would cause flare. The image would be effectively lifted in brightness. Or you might get a specular reflection of some sort, and you might see on the screen a series of sort of splodgy circles caused by the reflection of the light in the lens. All of this is best avoided, and one way of avoiding it is to have a lens hood like that, so that the light which goes in at an angle is blocked by the lens hood, so that light can't enter, and the light at that particular point hits the inside of the lens hood and is less of a problem. For lenses which are zooms, it is more of a problem because of the change in the angle of view. You end up having a fairly wide lens hood, so although it helps, it doesn't help a lot. And if you look at photographs of cameras in use, they will often have some sort of flag arrangement to try and block out the light at some particular angle, often made out of cardboard and gaffer tape. This is a modern zoom lens. I took this picture a few years ago at the London Olympics, and it's one of Canon's Wonder super lenses. It's got the glass on the front, is like a dinner plate, and it has an enormous 100:1 zoom range. And not only that, it's got a 2x range extender. So by using both the zoom angle and the range, this hasn't come out too brightly here, but the maximum angle of view there is focal length, rather, I beg your pardon, is 9.3 millimeters, which is really quite wide angle. going to 1.8 meters focal length at the other end, which is not so much more of a zoom lens, more of a telescope. Really quite a fantastic piece of glass. And modern computer design of lenses has eliminated a lot of the artifacts that lenses used to, and to a certain extent still suffer from. So here are some of the deficiencies. I started looking at the deficiencies and it got to be quite a long list, so I'm going to rattle through a few of the more interesting ones quickly. The first problem is poor resolving power. MTF is modulation transfer function, which is fairly meaningless, but you might look upon the lens as a low pass filter. The next one is portholing and shading. If you have a cheap lens, you may notice at the corners of the screen it's less bright. This is called portholing. And if you pay a lot of money, it's not too much of a problem. But the I thought it had gone out again. Shading. The lens may not transmit the light equally over its field of view. It may be darkish at one side, or even more annoyingly, it may be pink or green at one side, and there may be a colour cast. Which brings us on to chromatic aberration. Now, when you have a lens and you see the drawing, as we saw earlier, with the subject and the image is nicely focused on the plane, well, that might be fine for, say, green light, but for blue light you might end up with a different result. So the focal point for blue light is different, as the focal point for red light might be different, and this is called chromatic aberration, where you have a range of focal points according to the wavelength of the light. And if you pay a lot of money, it's less of a problem. Barrel distortion is one of the things that annoys me. You often see it. And a wide-angle lens, the extreme example of which is a fisheye lens, a vertical, which you would expect to be vertical, isn't, and it's curved like that. And you'll see it all the time on television, because the ENG camera with his wide-angle lens means that it gets a wide-angle shot, and it's all easier to do. But the knock-on is that the verticals are bent, and the person he's looking at, if he's too close, his face will be distorted, his nose will be big. Just watch and you'll see it. The reverse of which is pincushion distortion, where the verticals are bent like that. But you don't often see that because it's less of a problem. Flare we've spoken about. Unwanted UV or infrared transmission if the lens ideally should be a bandpass filter, whereby it stops infrared light and it stops UV light, because these will, especially infrared, can overload a CCD sensor because they do have response into the red. Then there's coma, astigmatism, spherical aberrations, and I stopped at that point. So lenses can be deficient, and all these things affect the quality of your picture. And that's probably about it. So are there any questions? Yeah, go on, Henry.
Basically, when you see a plane,
Just hang on for a sec.
I'm sure you'll need it. When you see an aeroplane with a propeller, you often see the blade is bent, and you obviously know that it's not. If it was a shutter, it would take an instantaneous microsecond or millisecond exposure, and that would be actually straight.
Yes.
It's because it's moved. I reckon the shutter is variable as it goes down the picture. Is that possible? You get it with helicopters as well as airplanes.
I think what you're seeing by the bend is the actual movement of the propeller forward during that interval of the
Well, if that was so,
of the light.
if the exposure was for that particular period, surely the top would be blurred and the inside would not.
No, it's because of the scanning going down.
Exactly.
Yeah.
Yeah, but that exposure must, the exposure or the capture period is a different time as it goes down the vertical frame.
Am I really?
Take this,
Yes.
offline?
Yes. Well, I've just, the hooked has just pulled me off to one side. Thank you very much, chaps.
So take it at lunchtime.